This next lecture is on power series, how we form them. It's a bit of a bridge between the idea of a polynomial and then an infinite series, and so you see the dots here at the end of all of these, and that's the idea of an infinite series. We also have this idea of interval of convergence, that is that these are power series for different functions. However, they don't converge unless you're within certain bounds. Of course, some of them have an infinite radius, which we'll get to, some of them a finite radius. And we can see that graphically. If we look back over here, in this case, for instance, if I use cosine, here's the plot for cosine, and as I use higher and higher degree approximations, it looks as if I'm going to approximate this better and better. So it turns out that you can prove that if you go higher and higher order enough, you can go out as far as you want. Whereas for something like tangent, that's not going to work. Here's the plot for tangent, and then if you increase the power series degree, you'll get better and better to that one particular period of tangent, but there's never any way you're going to get basically beyond the asymptotes to get over to here. So sometimes the asymptote is what gets in the way, but sometimes it just doesn't get beyond a certain value. And so we have these power series which we can find for different functions, and we'll be using these quite a bit in later sections. However, sometimes they're finite intervals of convergence. Okay, so what we see here then is different Taylor polynomials, really Maclaurin polynomials, centered 0 of e to the x. And then the idea that these are approximations, but we can really represent e to the x exactly, theoretically, if we go on forever to this infinite series. And so this is your actual definition of a power series, and sigma notation becomes much more useful here because, especially, of course, if we're going out to an infinite series and we want to write it in some more compact form, we're centering it at c in this way. And so the way we got our a0, a1, a2, and so on, all these coefficients in the previous section on Taylor polynomials, was by using derivatives and factorials. So, power series centered at 0, we can see that because this is x minus 0 to the nth. This one's centered at -1, it's x minus -1. This one's centered at +1. So that's where you can center these things. As far as the radius and interval, though, there's three different ways this can come out. You can either have the approximation only work exactly at the center and nowhere else. You can have a finite radius. It's called a radius because it actually works in the complex plane, that we're going to confine ourselves mainly to real numbers. Or it can have a radius which is infinite, so it converges along the whole real line, which we saw for, say, sine and cosine, for instance. So those are our three possibilities. Only at c, a finite value, and everywhere. All right, so if we have n factorial times x to the nth, the way we discover where these things converge is just use the ratio test. So a lot of series convergence and divergence tests we've learned, but we're going to only use ratio test here, at least initially. So the limit as n goes to infinity to the n plus first over the nth term, and you set it to be less than 1 and find out what x has to equal for this to be true. So when you put in the n plus first over the nth term, we cancel to get down to here. I can take the absolute value of x out because the limit is only with n, but this goes to infinity, this limit. So therefore, this would only be less than 1 if x was equal to 0, and so basically it only converges at its center. Its radius is 0. Here we have 3 times x minus 2 to the nth, so you do the ratio test again, n plus first term over the nth term. Everything cancels except getting down to absolute value of x minus 2. As n goes to infinity, it doesn't expect this because there's no n's left. So we set this answer to be less than 1, and so therefore our radius is 1, and actually our open interval of convergence would be centered at 2 with a radius of 1, so it's from 1 to 3, and we'll get back to the endpoints later. Here we have actually the series for, I believe this is the series for sine, and so you do the n plus first term over the nth term, and if you take this limit, it goes to 0, so regardless of what x is, the limit goes to 0, which is always less than 1, and so therefore your radius of convergence would be infinite, or the intervals from negative infinity to infinity of convergence for this power series. Now we talk about endpoints. So as I mentioned, if it's a finite interval of convergence, you've got to check the endpoints. Maybe they're open on both sides, maybe on the left or on the right, or maybe they're closed on both sides. So you do the same thing we just did a moment ago. That is, you do the n plus first term over the nth term for the ratio test. Things will cancel out. If you get a finite interval of convergence, non-zero too, of course, like in this case, absolute value of x has to be less than 1, so we're -1 to 1. Then what you do is you take those endpoints and you plug them back into the original series. So if you plug positive 1 in here, 1 to the nth is just 1, you get down to the harmonic series, which diverges. If you plug in negative 1, the other endpoint of this interval, into the original series, you get the alternating harmonic series, which converges by the alternating series test. So therefore the overall interval of convergence is negative 1 to 1, but it's closed at negative 1, open at positive 1. Another example, we can see this is going to be centered at negative 1 because of the x plus 1. If you do the ratio test, rather complicated at first, but then quite a bit cancels out. You get all the way down to here. Setting this to be less than 1, what you end up getting then is an open interval from negative 3 to 1. And so plugging in negative 3 in for x, negative 3 plus 1 is negative 2. The negatives cancel. 2 to the n over 2 to the n is 1. It diverges by the nth term test. If you plug in positive 2, things cancel out, and you get a divergent series because it basically oscillates, and so therefore both endpoints diverge, and so your interval remains as the open interval from negative 3 to 1. Here we have x to the nth over n squared. From your experience with p-series, you might suspect this converges on both sides, and it does. So doing the n plus first over the nth term, things cancel out till we get down to absolute value of x is less than 1. So we go from negative 1 to 1. Whether you plug in negative 1 or 1, either way this is going to converge, and so it converges on both sides. I'm not going to go through too many details here. Suffice it to say that when you differentiate and integrate power series, it never changes the open interval of convergence. So that is the radius of convergence. When you differentiate or integrate a power series is always the same. The endpoints may change, the interval of convergence may change, but the actual radius, that is the open interval, will never change. And we'll be doing a little bit of differentiation, integration of these to get to their approximations. So they're just showing the idea that for this series you can integrate it, you can differentiate it, and in each case you can check endpoints to see how those might have changed, but the open interval is always going to be from negative 1 to 1. Here's just one more example of finding the interval of convergence. The series was, let's see, I've already put in the ratio test, so the series originally would have been x minus 1 to the n plus 1 over n plus 1. So here we have our n plus first term times the reciprocal of the nth term. We can cancel the x powers and put the absolute value of x minus 1 in front. We have the n's left over here. This limit becomes 1, so we're left with absolute value of x minus 1. We set it to be less than 1, so here's then our open interval. If you take 0 and plug it into the original function, you've got negative 1 to the n plus 1. Negative 1 to the n. So actually this was an alternating series. I should go back and add that in. So these would cancel. You'd have 1 over n plus 1, which diverges. You could do a limit comparison test with p-series, p equals 1. If you were to plug in 2, then you'd have negative 1 to the n plus 1 from the original series, and then 2 minus 1, so 1 to the n plus 1, which is just 1. And now we have something similar to an alternate harmonic series. So this converges by the alternate series test. And so therefore, your overall interval of convergence is 0 less than x less than or equal to 2.